Okay, people, welcome back from the break. We're just going to do a little bit with gravity here. We've been talking about gravity in space, right? Giant nebula with giant areas of dust and gas, and just so massive that there's a crazy amount of gravity there, producing stars. So anyway, you guys have had gravity, I'm sure, since probably elementary. Okay, so I'm not going to really beat a dead horse here and go into it over and over. But I will also add tides, Earth's tides. Most people don't know what Earth's tides come from. So I'll just add a little of that at the end, and that will be it. You'll ask a few questions. Okay. So gravity, I think most all of you already know what causes gravity: the size of two objects. It's the attraction between two objects. Okay. The thing I've mentioned before called space-time. What's in space? Not emptiness, space-time. It gets scrunched. It gets kind of deformed, and that produces gravity. So the bigger the two objects, the greater the force of gravity. Okay, so Earth is pretty big, so we are pulled towards it, and actually we pull Earth too. You can technically give it a measurement, but it doesn't really mean much. And the force between two people, there is gravity between them. If you go out into space, you will be able to see, if you're close enough, there will be a gravitational pull between the two people. So it's everywhere. So the size of the objects and the distance between them is what produces gravitational pull. Similar to magnets, really. Bigger magnets have a stronger pull. One can be bigger, but it doesn't matter, one or the other. In combination, it produces gravitational pull. And then also the distance between them, like magnets. Very similar kind of behavior. Okay? So I have a couple of quick videos to use with this. You'll answer a couple of questions. If you're on the moon, what two objects are producing your weight? And why are you lighter on the moon than when you are on Earth? In other words, why is gravity less on the moon? So you'll just answer those. And then I'll have a brief video about this ocean tides and gravity. You're actually seeing what gravity looks like in space-time from the ocean's tides. Okay, so let's go over to those. This one is a nice video
that pulls any two objects together,
showing what gravity is. A nice graphic. I like this graphic.
You're pulling on the Earth, the moon, the sun, and every single star.
So
and they're pulling on you.
Drawn to each other, and the bigger they are,
the stronger its gravitational pull.
That's probably
the
a computer simulation.
The lower its
probably.
If every mass
so the bigger the things are,
mass in the universe, no matter
the more
how
they
small,
pull toward each other. You guys know this
changes in
already.
gravity can tell us about what those objects are doing. Fluctuations in the gravity coming from the universe.
Okay, so this is another topic. We're not going to worry about that. Now I'm going to go to the ocean's tides. How tides work. I don't think I'm going to need to see all 5 minutes of this. But it's a good, simple explanation. Tides going up. It's a time lapse. And that's actually from the Earth rotating. The water doesn't move as much. It's the Earth rotating through two bulges in the oceans. It's not really the water moving. Earth's rotation through these bulges. Okay, gravity. I like that. That's some kind of nebula right there.
Here's the Earth rotating on its axis every 24 hours. We'll now draw the Earth as a diagram with its surrounding layer of ocean. And to the right is the silvery moon.
Okay, so if there was no gravity, the water would be evenly distributed through the oceans. And of course there's land, right? We have land masses sticking up through the oceans, of course.
And the Earth is equally attracted to
so
the moon.
Even pull, technically the gravity is the same.
Notice that the two force arrows are the same length, showing the gravitational attractions are of equal strength. The moon pulls on the ocean closest to it and makes it bulge
he's just
outwards.
starting his graphic here. Actually, he's just giving you an example. This is not how it looks, actually. This is how gravity would look if there was if gravity didn't squeeze. Gravity actually squeezes and what was the word I used, guys? Stretches out things. So actually, real gravity, he'll show, stretches out oceans on both sides and squeezes in. That's actually what gravity really does. So you know something others don't. Oh, come on now.
And a low tide where the oceans don't bulge.
This is the false impression. This is not correct. This is not how it looks. Low tides will be on top and the bottom being squeezed. And there'll be a high tide here and a high tide there being stretched.
How come?
Now he's explaining.
Greater when objects are closer. We'll call the location of the ocean on the near side of the moon, point A, at the center of the Earth, point B, and at the far side ocean, point C.
So he's going to show that gravity actually pulls more here, closer, the distance is closer, and then here on the backside of the Earth, the distance is farther, so the pull is less strong to the moon. And what that ends up being like is like the same as being stretched, actually. So this will be not pulled, the water will not be pulled as much here, and the Earth will be pulled a little more, and this water here is closer, so it'll be pulled even more, and it ends up being the same as being stretched.
The strength of the moon's gravity is strongest at A because it's closest to the moon. So the part of the ocean that bulges towards the moon most is at A. But the moon's gravity also pulls on the Earth, moving it
here
towards
is a little
the moon
farther,
as well.
so it's not pulled as much as this closer water. So it moves a little bit. And then this water back here is farther than any of these two. So the force of gravity is not as strong because the distance is farther away. Similar to like a magnet. A closer magnet would be pulled more distant magnet would be pulled less. So it's pulled, but only a little bit. And altogether, it ends up being the same as being stretched. So this is the high tide on the front and the high tide on the back. And as we move, as the Earth rotates, it rotates through these different elevations of the tide. So you think the ocean is actually rising and falling, but it's not. You are moving. We are moving through lower elevation. We're moving through a higher elevation, and so it looks like tides. So in the end, it's stretched. Gravity in the end ends up stretching objects and also squeezing objects. The same is happening on the moon. The same thing is happening there. But there's if there was water on the moon, you'd see the same thing. It'd be, the water would be farther out here, higher elevation, and on the back it would be farther out. And on the top and the bottom it would be squeezed
By the time the Earth has rotated once
and then so we follow the moon through its cycles. And that is how our high tides work. So this high tide, this bulge will end up being closer to the moon, and this back will be away from the moon.
That means that the Earth has to catch up with the moon. So
don't worry about the catching up part. So that is actually how our tides work.
Or check out some
so the Earth is spinning and moving through this higher area of elevated tide. And then the Earth is spinning, you are spinning away from the elevated tide to the lower elevation of tide. So that's pretty good.